Section 6.5 introduces kinetic energy and the work energy theorem. Here we want to understand the connection between work and speed, and then use the work energy theorem to solve for some different problems. A useful application of work lies in the work energy theorem. Basically, this says that if you have work that's done by some sort of a net force on a particle, and you can calculate that amount of work done for a given displacement, then the change in speed is actually very easy to find. We can get around all of those old kinematic equations with the work kinetic energy theorem. In the past, we had to analyze problems with the forces that were acting on something, look at that net force, set that net force equal to an ma, solve for an acceleration, and then once we had an acceleration, we could go back to those old kinematic equations to solve for a vf. What we're looking at here is the ability to get around that. So remember, we said that work was equal to the integral of the force with respect to a displacement. So we had that from our past sections. What we're going to do now is we're going to take this amount of force, and since force is equal to ma, we're going to replace that in the integral. So instead of an f, we have the integral of ma dx. We're going to rewrite a as the derivative of velocity with respect to time, and then stick in basically a 1, a dx over a dx. Notice that we wrote it in a slightly different place, but essentially that's all we're doing from this step to this step, is adding in the dx over a dx. What that means is that one of these dx's can actually cancel. We then have a dv, which you see left over here, and we also have a dx dt left over. That dx dt can be written as a velocity, and the m, of course, is still there. So now we have an integral of mv dv, where we could now change our limits on the integral sign to an initial and a final velocity that the object is moving with. When we integrate this, again, we raise the power on the variable by 1, so the v is now going to be squared. We'll divide by a 2, and we basically have 1/2 mvf squared minus a 1/2 mvi squared for that net work that is done. So note that in this derivation, we did assume that the dx, or the displacement of the object, or that force, was the same as the particle. This would only be true for rigid objects, so we were still under a rigid object assumption as we utilize these equations here. And this really reveals an important quantity, because this 1/2 mv squared is something that we have seen in the past. That's what we call kinetic energy. So we do see that equation here. Kinetic energy is equal to a 1/2 mv squared, and is basically the energy of anything that is in motion. So anything that has mass and a velocity would have a kinetic energy to it. The units for this is the same as work, so the units are still joules on kinetic energy. And like we said, it's really just this energy of motion. Now we can look at the work kinetic energy theorem, or the work energy theorem, that basically says that when work is done on a system, and the only change in that system is a change in its speed, basically it got faster or slower because of that work that was done, then that work is equal to the change in the kinetic energy. So essentially, we can set net work equal to this delta K, or the 1/2 mvf squared minus the 1/2 mvi squared. This can become quite useful in analyzing various problems. So let's check our understanding just a bit. If the speed of a particle increases, would the work done on that particle be considered positive or negative? That answer is positive. Increasing speed is going to be a positive amount of work. If the work done is negative, what would that now imply about the speed? If you have a negative amount of work done, that's going to imply that you have a decreasing velocity. So if the work increases the speed, causes something to get faster and faster, that's positive work done on the object. If the object is slowing down, that work is considered to be negative amounts of work. And remember the spring that could go from some negative x max to some positive x max, basically compressing the spring and allowing it to bounce back and forth and oscillate between those two compressed and stretched positions. Here, the work would be equal to 0, because you'd have equal amounts of positive and negative work done by that same force. Again, it would be like a graph that has the same amount of area above the axis as you have below the axis. And again, that would be a total net work of 0. So even though speed here is constantly changing, the theorem is really showing us that it relies on just the initial and final speeds of the object. It does not depend on the details of the path followed between those 2 points. So when utilizing that work kinetic energy theorem, that work is the change in the kinetic energy, or the difference between these 1/2 mv squared quantities, really all you're looking at is the initial and final speeds of the object. Everything in between, no matter how this thing might change its speeds in between, we really only care about the final speed and the initial speed that the object is moving with. In the next section, you'll see me do a few examples so that you can try these out and see how we can apply this theorem to help us solve some problems.